Sample problem number 3 represents the third type of projectile motion problem, one in which an object is launched at an angle but above the ground as well. Let's read this question. A golfer is trying to improve the range of her shot. To do so, she drives a ball from the top of a steep cliff, 30 meters above the ground, where the ball will land. If the ball has an initial velocity of 25 meters per second and is launched at an angle of 50 degrees above the horizontal, determine the ball's time of flight, its range, and its final velocity just before it hits the ground. Before even attempting any of these problems, I want us to identify the x and y components of the golf ball's initial velocity. So the golf ball's initial velocity has a magnitude of 25 meters per second at an angle of 50 degrees to the horizontal. The x component of this velocity would be this component vector, which we will call Vix, and the y component of the velocity will be this component vector we call Viy. Vix represents the adjacent side to 50 degrees with respect to the hypotenuse 25 meters per second. When we are dealing with adjacent and hypotenuse, we are looking at the cosine ratio. So the x component of the velocity is equal to 25 cos 50 degrees. To two significant digits, the x component of the projectile's velocity is 16 meters per second. That's positive 16 meters per second. The y component of the object's velocity is the opposite side of this triangle with respect to the angle 50 degrees and the hypotenuse 25. So we can calculate it by writing 25 sine 50 degrees. To two significant digits, this becomes plus 19 meters per second. Now that we've found the x and y components, we can attempt to answer the question. In the first part of this question, they ask us to find the time of flight. Whenever we're solving for the time of flight, we want to look in the vertical or y direction. So we need to collect all information we know about the y direction. We've just calculated the y component of the velocity is plus 19. We know the acceleration in the y direction is negative 9.8. In this type 3 example, the object ends up with a displacement of 30.0 meters down. So we can say delta dy is negative 30.0. And our job is to find delta t. We use equation number 3 as it incorporates every variable that is given and every variable that's required. Delta d is equal to v1y delta t plus 1/2 ay delta t squared. Now we're trying to solve for delta t, and delta t appears twice in this equation, once here and once over here. In previous examples, for type 1 and type 2 projectile motion, we were allowed to simplify this equation based on the information given in the question, and it allowed us to avoid using the quadratic formula. But in this situation, there's nothing we can do to simplify this, so we need to use the quadratic formula. The quadratic formula, using the variables in this question, would be delta t is equal to negative b plus or minus the square root of b squared minus 4ac all over 2a. So we have to prepare this equation, sub in what we know, and rearrange it so that we get our coefficients a, b, and c. Let's do that now. Negative 30.0, and I'm going to omit the units just to keep this simple. Plus 19 plus 1/2 negative 9.8 delta t squared. I'm going to bring this negative 30 over the equal sign so that we're left with all of the terms on the right hand side. 0 is equal to 30 plus 19 delta t. And I'm going to simplify 1/2 times negative 9.8. So this becomes negative 4.9 delta t squared. In order to make this look like a quadratic equation, I'm going to bring the negative 4.9 t squared up front plus 19 delta t plus 30. So we have our A, our B, and our C. Using the quadratic equation, you should get two values for delta t. If you punch this in properly, you should get negative 1.2 seconds and positive 5.1 seconds. It becomes apparent that we need to reject the first value, as we cannot have a negative value for time. So the time of flight in this problem is determined to be 5.1 seconds. Part B, determine the range. The range is a horizontal displacement of this projectile. So we're looking in the x direction. So we need to collect all information that we know in the x direction. We determined our initial x component of our velocity to be plus 16 meters per second. And we know our time of flight is 5.1 seconds. Therefore, we can quickly find our range using what we've called the range equation, Vix delta t. So this is 16 multiplied by 5.1. If we punch this into our calculator, to two significant digits, we get positive 82 meters. So we say the range is 82 meters right. We've replaced the positive sign for the direction right. In part C, they want us to find the final velocity. Now this is important. This is the first time we've determined the final velocity of a projectile. Now the final velocity of any projectile has the same characteristics, and when solving for final velocity, you will use the same steps. So it's important that we underline this title, star it, and even highlight it, because we'll come back to this problem to review how to find the final velocity for any projectile motion. Take a look at the diagram, and it's easy to see that the final velocity of a projectile, of any projectile, has the same basic shape. It is downward and on an angle. So when solving the final velocity of a projectile, we'll need to determine the final x component of its velocity and the final y component of its velocity, as well as the angle it is making in order to report the direction. So let's begin. Our first step is to find the final y component. So we need to find v2y. We need to collect and gather all of the information in the y direction. We know that ay is negative 9.8. We know that delta dy is negative 30. And we know that the time of flight was 5.1 seconds. We also know that v1y was positive 19 meters per second. So we have a bunch of variables, and we can use more than one kinematics equation. I'm going to use this one, equation number 2. v2y equals v1y plus ay delta t. It's simple, and it allows us to solve for the final y component of the velocity. So we sub in, we have plus 19 plus negative 9.8 times 5.1. If you punch this into your calculator and report your answer to 2 significant digits, you should get negative 31 meters per second. The negative sign implies that the final y component, just as we have drawn, is in the downward direction. So we can say that v2y is negative 31 meters per second. In the second step, we'll find the final x component of the velocity. And now this is really easy. The final x component is always equal to the initial x component, and in this case, it was plus 16 meters per second. So remember this. The reasoning is the horizontal component of a projectile's velocity never changes. And this is an important characteristic of projectile motion. Once you've determined the final x and final y components of the velocity, you're going to construct a simple right-angled triangle with these values. So this right-angled triangle will look like this. 31 being the y component, and 16 being the x component. And the final velocity is this vector right here. We can calculate the final velocity using Pythagorean theorem. It's equal to the square root of 31 squared plus 16 squared. If you punch this into your calculator to 2 significant digits, you should get 35 meters per second. So we're almost done. We've identified the magnitude of the final velocity, but we haven't given an indication of its direction. In order to do so, we need to find theta, the angle which with this velocity is making. In order to find the angle, just as we've done in previous examples, we're going to use trig ratios. We can state that theta is equal to the inverse tan of the opposite over the adjacent. In this case, the opposite to the angle is 16 and the adjacent is 31. If you punch this into your calculator, you end up with an angle of 27 degrees. So now it's time to report our final velocity with both its magnitude and its direction. We said its magnitude is 35 meters per second, and its direction is 27 degrees to the right of down. Use these steps to determine the final velocity of any projectile motion.